Okay, and today we are going to discuss nonlinear models. Before we talked about linear models, linear models assume, again, like a zero or constant rate of change. Nonlinear models have variable rates of change, meaning that they don't change at the same rate or the same value each time. So one time you could decrease, say, by 2, in the next step you might decrease by -4, and then just continue to change at a different amount, but the amounts should all be related. Okay, that is our goal with nonlinear modeling. Okay, so we have an example here. So in a country, they start out when we start studying them at 2 million people. In any given year, we have a birth rate is half of the current population, and death rate is 1/3 of the current population. So half of the whatever the population is at for a given year, the amount of births is half of that, and the number of deaths is 1/3 of that. Okay, so our job is to determine a mathematical equation, or a model, essentially, that describes the change in population. Okay, we need to introduce some notation here. Again, it's math. We need to make sure that we communicate our ideas in a mathematical form, but also that they have connection to whatever context we're working in. So I'm going to say let P of t be, so this is going to be the population t years after study. Okay, and I'm actually also going to add population in millions, just so I don't have to write all those zeros out. Okay, so in part A, we want to determine a mathematical model that describes this change in population. Well, the change in population, that's looking at P prime. Okay, so how does the population change? Well, we know that in any population, there's going to be bursts are going to be a positive. So bursts are going to increase our population, and then whatever the number of deaths are, those are going to take away from our population. Okay, so heuristically, our change in our population should be represented by the number of births minus the number of deaths. Okay, and in our problem setup, we're actually given some information about the birth rate and the death rate. Okay, well, if I look at the birth rate, it says the birth rate is half of the current population. So this part, that becomes 1/2, and then to represent the current population, well, population at t years is just given by p. Okay, and then the number of deaths, let's see, the death rate is 1/3 of the current population, so that should be minus 1/3 of p. Okay, and then if I have like variables, so I can simplify this to get 1/6 p. So this means that the change in population is equal to 1/6 of the current population, and that's a positive value, meaning that this country is growing over time. Okay, so that's our change in population. Now, in part B, it says complete the table below. Okay, and we're given time at 0, 1, 2, 3, and 6 years that we have to determine. Well, at 0, it's 2 million people. Now, at time 1, that means that after the first year, we want to determine what is the population. Well, we know how the population changes, right? So if I know that the current population is 2, I can insert 2 into P to determine the change. Okay, so the change here, P prime, is going to be 1/6 times 2, which is 1/3. Okay. Now this is an increase to whatever the current population is. So this should be 2.33 and then continuing million people. Okay. And continuing this pattern. Okay, and continuing this pattern, I can do the same thing over here. So P prime should now equal 1/6 of 2.33. Okay, and punching that into my calculator, I get 0.388 or so. And so adding that, I should get 2.718 or so. Okay, and I filled out the value for 3. Now, instead of doing this all by hand, Excel is really nice to be able to do all this for us. So here I've created just a little mini table of T, P of T, and P prime. So the change in P, the change in the population. So I've inserted our table, instead of horizontally, I've inserted vertically. Given the T values that I want to know about, and P of T here is 2. Okay, P prime. Now I'm going to actually insert the P prime value that we found down here of 1/3. I'm going to insert this formula actually to right next to the 1, because that's where I want to that's the value that I want to add to my previous P of T to get the new value. So I'm going to insert a formula by doing equals, selecting the cell that I want to know about, and then my rate of change was 1/6 of this, so I'm just going to multiply this by 1 divided by 6. Okay, and I get out 1/3 just as I found out. Okay, now to determine P of T, what did I do? I took my previous value, and then I added to that whatever the rate of change was. And so I'm using cell referencing here because my goal is I want Excel or any other computer software to do this for me. So I hit enter, I get out the 2.33. Now to carry this formula down for us, I have to select both cells, and then in the lower corner there's a little black box. Hover over it until you get a black cross, drag it down, and you should get the same values that we got over here. And actually Excel might be a little more accurate than what we did on our calculators. So I can go ahead and fill this in, and I got, let's see, at 6 the population should be 5.04 million people. Okay, so after 6 years the population has increased a lot. Okay, so the next question says, based on our observed pattern, determine the population after 5 years of study. Well, we did it in Excel, so it's kind of cheating. But what we did was we always took 1/6 of the current to get, and added that to our previous one. So I could just do that same pattern, and I eventually get that P of 5 is equal to, it would be this. Okay. In part D, so it says graph the result from part B. Okay, so really what it's asking us to do is to take a graph of these values. Okay, and so I can do that. Okay, so I'm going to go to my Insert tab in Excel, and then I'm going to make this bigger for us to see. And then if I go to the Insert tab, go over to the Charts section of the ribbon, go to Scatter, and then insert just a scatter plot. I want the labels in there. Let's try that again. So I'm going to highlight everything here, just T and P of T. Go to Insert, Scatter, plot those. Okay, well that's the graph of just those 6. And then let's see, what's it asking? What type of equation best describes the data. So I can actually see, well, the data actually looks to me kind of linear, but in reality it's not. So I went ahead and I went up to 25, and I'm going to insert the same graph. So I'm going to insert scatter, and if I make one with more data points, this actually looks exponential. Okay, and that typically populations follow an exponential model. Okay, so really the answer here, even though it looks to be somewhat linear, it's actually going to be exponential. So an exponential equation. Cool. And remember, we can almost rule out the fact that it's linear, because our rate of change we determined to be 1/6 of our current population. So this was a variable rate of change, meaning that the rate of change changes at different rates. And remember that a linear model had a constant or zero rate of change. Okay, so writing an equation that describes the population t years after initial study. Well, the basic exponential model follows this equation. P is equal to P naught, which is our initial population, e to the kt. Okay, so we can go through and find, well, our initial population we said was 2 million. Okay, and then k is actually going to be whatever our rate here is, and we'll see this when we study differential equations, but for now the k value will be whatever the the constant of proportionality is in our rate of change equation. So this will be e to the 1/6 t. Okay, so key ideas here is that when you see an exponential, or when you have a model that changes proportional to the variable of or the dependent variable, this is going to be an exponential model, and the exponential model basic solution is this equation. Okay, so that's a basic rundown on nonlinear models. There are other types. We just are going to focus on exponential models here.